All right, so question 15, right? How many chiral centers are there in ampicillin? To have a chiral carbon, we have to have 4 unique substituents, right? So number 1, you cannot be sp2 hybridized and be chiral, because if you're sp2 hybridized, like these carbons here, that essentially means you have 2 bonds to the same thing. You have to have 4 different substituents. And so if we look at this carbon right here, right, I've got this amine, I've got this hydrogen, I've got this benzyl or this phenolic ring, right? That all 3 of those are different. And then if I look to the right side of the molecule, all that right side of the molecule is also different. So we have 4 unique substituents on this carbon, right? The the amine, the hydrogen, this phenol, and then the rest of this structure. All 4 of those things are different. That makes this carbon chiral. You have to have 4 substituents. So the nitrogen can't be chiral, right? That amide, carbonyl can't be chiral. But we do have one more. We have a few more actually, right? This carbon right here within that beta-lactam ring is chiral because I have a hydrogen. I have everything to the left, which is different than everything to the right, which is different to everything down below. So that carbon is also chiral. Right, to the left, I have a nitrogen. To the right, I have a carbon. But if we look, this carbon is attached to a sulfur. It's attached to this different part of the ring. It differentiates itself from this carbon because this carbon's in a carbon-oxygen double bond. So even though they're both carbons, they are not the same carbon, right? They are different carbons. So far, 1 chiral carbon, 2 chiral carbons. This carbon is also chiral, right? The next carbon down is chiral because, right, hydrogen is different than sulfur, is different than nitrogen. And then again, what I have to the left is different. So that's my 3rd chiral carbon. And my 4th chiral carbon would be right here next to the carboxylic acid. Same thing, right? I've got a hydrogen that's different than this carboxylic acid, which is different than this dimethyl carbon, which is different, right, than the nitrogen group in that direction. So we end up with 4 chiral carbons in this structure, right? We need to have 4 unique substituents. So we can't be sp2 hybridized, right? So we've got 1, 2, 3, and 4 chiral carbons. This carbon can't be chiral because I have 2 methyl groups, right? 2 of the same groups. I need to have 4 unique substituents to make that chiral. Yeah.
All the errors and stuff. If there was like
This carbon right here.
yeah, there was like another attached to the X that would knock it out of it.
This would somehow have to be symmetrical. So even if this was a carbon to the left, it would still be chiral because you would keep going until you find a difference, right? So even if this was carbon, this is carbon, and this is carbon, they're all different carbons because this carbon is a sulfur, is attached to a sulfur. This one's carbon-oxygen double bond. This one, if this was a carbon, then it's next to this carbon-oxygen double bond, right? They would be all different. Like in order for it to, those are different. In order for it to not be different, right? Like an example, would be like if we had a 6-membered ring, and maybe this will help kind of give you an idea of what I'm talking about in like the symmetry. So you might think this is chiral, right? But I've got an oxygen, I've got an alcohol, I've got a hydrogen. But then if we look to the left, right, carbon, 2 hydrogens, carbon, 2 hydrogens. So we keep going, right? Carbon, 2 hydrogens, carbon, 2 hydrogens. We keep going, carbon, 2 hydrogens, carbon, 2 hydrogens. So like here's a case where we have, you might think that's chiral, but we have symmetry. We have to have it be exactly the same for it to not be chiral. So even if I put a carbon there, that's not the case because the rest of this molecule is totally different. The left side of this molecule is totally different than the right side of the molecule, right? There's no internal symmetry in that molecule, and that's what we'd have to have for it to lose chirality. Like it would have to be exactly symmetrical, that position. Any other questions on that chirality? All right. Do we want to go to question 6 for Zoom here, or?